This is lesson 3 of unit 5 on exponents. Specifically, this lesson we will be investigating exponential relationships. So we have a bit of a task here to start out. So it says the temperature data collected by a temperature probe has been recorded in the following table. Calculate the first differences, calculate the second differences, calculate the ratio, and plot the coordinates. So calculating the first and second differences should not be new to us. But this ratio of y values is going to be new. So right in the question, it tells us what we need to do. So to calculate the first differences, again, you should know that we are taking the second, so y2 minus y1, right? y2 minus y1, etc. Until we have them all done. So we're just simply subtracting. So first one would be 6 minus 2 is 4. 18 minus 6 is 12. 54 minus 18 is 36. 162 minus 54 is 108. Sorry for the messiness there, I don't have a lot of space. And lastly, 486 minus 162 is 324. Okay, so we've calculated the first differences. Now we need to move on to calculate the second differences. And again, you should know how to do this because we did this in our quadratics unit. So again, we're taking first difference 2 minus first difference 1. So first difference 2 minus 1, 2 minus 1, 2 minus 1, and 2 minus 1. So we have 12 minus 4, which gives us 8. We have 36 minus 12, which is 24. 108 minus 36 is 72, and 324 minus 108 is 216. Okay, so up here again, I've completed 1, I completed B, moving on to C. So calculating the ratio of successive y values. So what that is asking us to do is to calculate the ratio of our first differences. Okay, so what that means, difference, anytime we see, ratio, we need to divide. So what we're taking is, and I'll do this in a different color again, 12 divided by 4. Okay, see where I'm getting those numbers? 36 divided by 12. Okay, and that would be 3. This would also be 3. 108 divided by 36, also 3. Did I miss one? 1, 2, nope. And 324 divided by 108 should also be 3. Okay, and with this box, we don't have another value, so that one should actually be shaded out as well. So, what do we notice here? We notice that all of these values in this column end up being 3, okay? So that's what's important to notice here, that ratio of successive y values, which again is just taking those first differences and dividing them instead of subtracting, should give you a constant number if you have an exponential function. So our last part that it's asking us to do here is just plot the xy coordinates. So again, to do that, remember that this chart, the original piece of this chart, this part of the chart, gave us those coordinates, right? So all we have to do is plot those on our graph. So we have 0, 2, and again, this is going to be a bit trickier because of our scale, but just do your best. That's going to be really, really close, excuse me, to the line there, and approximately there is where I would put it. 2, 18. So here we're going up by 25. So so we'll be, I don't know, somewhere in there. It's not going to be perfect. 3, did I miss 1? Yeah, I did. 1, 6. It's going to be somewhere close to the other one. 354, so just above that 50. 4, 162, so just above the 150. And 5, 486. So all the way up here somewhere. Oops. There we go. And of course we have to connect those dots to the best of our ability. So our line would look something like this. Okay, so to summarize what we should have learned there. So in an exponential relation, for equal steps of x, either the first or second differences are constant. For equal steps of x, the first or second differences, well, they're not constant, rather, are not constant. But the ratio, oh, sorry guys, it says neither. I'm just reading wrong. Neither the first or second differences are constant, but the ratio of consecutive y values is constant. And sorry, I probably confused you, but what that's saying is the first difference column here, the numbers are not all the same, right? Those were all different. When we calculated the second differences, those numbers were all different as well. So we knew this wasn't linear or quadratic. In order to determine if it is exponential, we took the ratio of those y values and determined that indeed this is an exponential function. Okay, so moving on here. So in terms of the graph, this graph is increasing rapidly, right? It starts very low and it shoots up extremely high. So that's as we move right on the x-axis, okay, and it's going to approach a steep line, right? It's almost going to become just like actually not steep, I want to say a vertical line, right? It's almost going to become a line that is going to be straight up and down, and we can kind of see that when we get to this part of our graph, right? It's almost a straight vertical line. Okay, so this is an example of an exponential relation. Okay, so in terms of terminology, so just some terminology for this lesson. What exponential growth is rapid growth represented by an exponential relation and a graph with a rapidly increasing positive curve. Okay, and maybe you just want to draw yourself a little bit of a sketch beside. This is when our graph looks like this. Okay. On the other hand, we could have something called exponential decay. So that's also going to be rapid growth. But this one is represented by an exponential relation, but the graph is rapidly decreasing. It's what we call spell, a rapidly decreasing negative curve. So those are going to look a little bit different than the one I drew above. So if it is rapidly decreasing, that means it's going to be really small over here and really big over here. And that's not the best. It will look something like that, okay? And of course, we should have arrows on all ends of this. Okay, so just draw yourself that little sketch so that you can understand what an increasing positive graph looks like and a decreasing negative graph. So this is the first half of the note. Okay. So an exponential function is a function with a variable in the exponent. So again, thinking back to our quadratic and linear, we know our linear just had an x in it. Our quadratic had an x squared. An exponential function, if we're looking at the equation, we know it's exponential if it has a variable as the exponent. So instead of being raised to the power of 2 for negative 2, it's raised to the power of x. So some examples of that: y equals 2 to the power of x, y equals 10 to the power of x, y equals 2/3 to the power of x. Notice in all of them, the variable is the exponent. Okay, so let's look at a couple more graphs here. So it says sketch the graphs of y equals 2x and y equals 3x on the same axes so that we can kind of compare them. So when you are subbing in these values, you are subbing it in as the variable. So you're replacing x with -3. And again, you could probably do this without your calculator because from our exponent rules, you should know that we have to flip that over to make that exponent. So it's 1 over 2 to the power of 3, and 2 to the power of 3 is 8. Okay, so you're replacing that x with the number it tells you. And I'm going to run out of space. 2 to the -1. Remember, anything to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And 2 to the power of 3 is 8. Okay, so let's start by graphing that one. And again, it's going to be a bit tricky with these fractions, right? But all you need to know is that those are bigger than 0 but smaller than 1. So just do your best to kind of plot those points as best as you can, okay? So we have -3, and we have our smallest number. So it's going to be basically touching that line, but not quite. That looks pretty good. Okay, same with the next one. It's a quarter of the way up through that line. It's a little bit bigger. This one's halfway up. -3, -2, -1. 0 is 1, so we're going to be right there. Then 1 is 2. 2, 4. Come on. And 3, 8. So 4, 5, 6, 7, 8. Okay, beautiful. Obviously, try your best here to connect those dots in a curve. Okay, beautiful. So again, you should be able to say, okay, this is a positive increasing graph, right? Because we can see that it has kind of that J shape versus that L shape, or U shape, I guess. Now we'll stick with L because it doesn't actually look like a parabola. Okay, so let's try the next one. I'll use a different color. So now we're going to do the same thing with y equals 3 to the power of x. So again, you are replacing the exponent with the x value it tells you we know that we can flip the fraction to make the exponent positive, so we don't even need to use our calculator here. Notice how my base isn't changing, it's just my exponent. And I did that wrong. Why do I always... It's only 3 to the power of 3 that I mess up. This is 1 over 27. This is 1 over 9. 3 to the negative 1 is 1 over 3. Anything to the power of 0 we learned is 1. 3 to the power of 1 will be 3. 3 to the power of 2 will be 9. And 3 to the power of 3 is 27. Okay, so again, you need to make sure that you're substituting those values incorrectly. The base is not changing. The exponent is changing. Okay, now we're going to go ahead and graph this. So again, it's going to be a little tricky because those are very, very, very small numbers, right? 1 over 27, if you typed that into your calculator, 1 divided by 27, that's 0.04. So very, very small. It's not even 0.1. So again, it's going to be lower than our 1 over 8, right? Our 1/8. So I'm going to draw it just as low as I can without putting it on that line. All these green dots should be just under, so this is a third. Just under our pink lines here. But 3 to the power of 0 is also 1. So it's going to be on that exact point of our pink graph. 2, 9. Oh, sorry, I missed 1, 3. So 1, 3. 2, 9. So 4, 5, 6, 7, 8, 9. And I don't think we'll be able to graph our 27. No, because we just don't have enough room. So again, I'm just going to connect those dots as best as I can. Putting arrows on both ends. Okay, so we can see that green graph, it increased even more rapidly than our pink graph, right? And we can see that the pink graph was 2x and the green graph was 3x. So maybe if we have a larger number out front, maybe that means we increase faster. Okay, so let's make some conclusions from this. So it says comparing to the general exponential function, y equals a to the power of x, is a greater than 1 or is a between 0 and 1? So we just said, well, a is 2 and 3, so those are both positive numbers. So a is greater than 1, right, in both of these cases. Okay, what is the y-intercept? So again, you should know this is your x-axis, this is your y-axis. So the y-intercept is just where our lines are crossing that y-axis. And we know that those are crossing at y equals 1 or at the coordinate point 0, 1. Okay, and lastly, are these functions increasing or decreasing? Again, looking back to the other side of your note, you should see that they are increasing because they have that kind of J shape. Those are increasing positive functions. Oh, and I missed one. Is there an x-intercept? No, right? We don't have any value for y being 0. So there's no x-intercepts for these. Okay, so moving on to a couple other graphs, that look a bit different. So again, it's asking us to sketch these graphs on the same axis. So this time we have 1/2 x and 1/3 to the power of x. So again, starting with our first one here, I'll choose different colors again. So remember what we're doing is we are replacing the x with the value it gives us. So we have 1/2 to the power of -3, but we learned that we can flip that fraction to make our exponent positive. So this would actually be 2 over 1 to the power of +3. And again, that makes it a lot easier, right? We can essentially do that in our head. 2 to the power of 3 is 8. Okay, so same thing here. 1/2 to the power of -2 is the same as 2 to the power of 2, which is 4. 1/2 to the -1 is the same. Again, flip the fraction, right? We don't have to write the 1 underneath, which is 2 to the power of 1, which equals 2. Anything to the power of 0, we know will equal 1, so we don't even really have to write that out. Okay, 1/2 to the power of 1 is going to give us the 1/2. 1/2 to the power of 2. Remember that 2 applies to both, so that's 1 times 1, which is 1, over 2 times 2, which is 4, and 1/2 to the power of 3. Again, the 3 applies to the 1, but 1 times itself is always just going to give you 1, and 2 to the power of 3 is 8. Okay, so now we're going to go ahead and plot our coordinates here. So -3, 8. So 1, 2, 3, 4, 5, 6, 7, 8. Put a point. -2, 4. 1, 2, 3, 4. Put a point. -1, 2. 0, 1. Notice how that's exactly the same as before. 1 1/2. 2 1/4. Oh, that should be a bit lower. And 3 1/8. So again, really close. Where are these lines? I want them to be dots. Really close to that 0, but not actually touching it. And again, our next step is to connect those lines, or sorry, connect the dots with a line. Whoops. Geez, I think I'd get better at this by now. Okay, so that is what our graph is going to look like. So moving on, let's graph this next one. Or first of all, figure out the points on the graph and then plot them. So again, when we have a fraction to a negative exponent, we can flip the fraction over to make that exponent positive. And I almost wrote 9 again. So that we can simply do it in our heads. Okay, so 1/3 to the -2 is the same as 3 to the power of 2, which is 9. 1/3 to the -1 is the same as 3 to the 1, which is 3. Anything to the power of 0 is 1. Anything to the power of 1 is just itself. 1/3 to the power of 2 is 1/9. And you'll see a trend here, right? We can basically just write 1 over whatever we got for -2. So the next one we can write 1 over what we got for the -3, which was 27. Okay, now that we have those points, we are going to plot them on our graph. So the first point is -3, 27, which again, I'm not going to be able to plot just because I don't have a large enough scale here. So I'm going to start with -2, 9. So -2, 1, 2, 3, 4, 5, 6, 7, 8, 9. -1, 3. 0, 1. 1 1/3. 1/9. It's going to be technically lower than our orange line there. And 1/27, which again is going to be basically on that axis because it's very, very close to 0, but it isn't actually 0. Hang on. This dot is going to mess me up here. Oh my goodness. There we go. That's not horrible. Okay, so again, we can see that that pink graph is steeper, right? It's growing rapidly to the left faster than the orange graph, okay? So again, notice that the orange graph is 1/2 to the power of x, and the pink graph is 1/3 to the power of x. So in general here, kind of making some concluding statements. So comparing it again to that general equation of y equals a to the power of x, is a greater than 1 or is a between 0 and 1? So here we have fractions, so we know that a is between 0 and 1. Okay, the y-intercept again is 0, 1, right? They have the same y-intercept, and we again don't have any x-intercepts. Okay, so these graphs are never going to cross the x-axis. And again, these are making kind of that L shape, so these ones are decreasing. Okay, and this is the end of the third note on the properties of exponential functions.